Hi, and welcome to another exciting edition of Lambert shading for pixel shading, as far as that goes. And my name is Nate Nestler, and this is Practice Studios. Now, before we left off of vertex shading for Lambert light model, but now we're going to do a vertex pixel shaded light model, and we end up with a better, smoother, nicer result. But the problem with this is that it's more computationally intensive because we're calculating per pixel or per fragment versus per vertex. So there's things to be won and lost in this scenario, but we do get a smoother result without a doubt. Now, if you were we do have to do some things a little bit differently for doing this compared to what we had to do for our Lambert vertex shader only, and not have to worry about anything as far as the pixel shading goes. So the key thing here is, well, first of all, just go ahead and copy your last. We'll copy your vertex shader, your Lambert vertex shader first, and then you're going to go here to create again and create a new effect, and let's call it Lambert_VS_ PS here for pixel shader, or you could do FS if you like for fragment shader. Either way, same thing though. Probably not have two sets of dates. You see, I've been copy and pasting a good bit here. Now you're going to have to add something new that we didn't have before. Now we had this one before for our projection matrix, but we're going to have to add something new, and this is going to be our world inverse transpose, and we need this in order to do our world coordinate system here. So go ahead and copy that and type this in. So it's going to be a float 4x4 matrix, and it's going to be world ITX and then lowercase f here, and then a colon. Now you can change the name if you like, but this works for our purposes here, because it is world inverse transpose. So instead of typing that whole thing out, that's just easier. And it is float values. So world inverse transpose, this is a special name. You do need to use it just like that says. Open less than sign, and then we're going to do a string here, and we're going to say UI widget with a capital UI W here, and then lowercase widget part equals in parentheses none, in parentheses, and then, sorry, not parentheses but quotes, and then semicolon, and then we're going to end it with a closing greater than sign and then semicolon. Okay, and now in the next part here, this is the same. This hasn't changed, and the reason why is because again we're not doing texture coordinates, so that's the same as before. This one here is a little different because we're no longer outputting the color, so to speak. We're not interested in color on our vertex shader anymore. So you'll notice our VS out is quite a bit different. We do have our float 4 position here. Now, if it was a float 3 before, make sure you change that to a float 4. It does need to be a float 4 for this. It is a float 3 going in, but going out it is going to be a float 4, and it has to be for these calculations to work. Same thing for the normal here. Note that this normal is a float 4, and be aware of that. Okay, so our float 4 here, and we have a position here, and we do colon and then capital position all the way, and then semicolon. And again, that is a special name scenario set up within the program for knowing the actual position of a vertex. And we are using curly braces, open and closing them for both of these, of course, as standard for structs, and then semicolon at the end. Alright, so float 3 here, object pose here, for the position of the object, colon, and text coord 0. Yes, we're using text coordinates. We're overloading the text coordinates, if you will, in order to get XYZ positions. And we can do that, and we have to do that, matter of fact, otherwise we can't make this work. And that's how we're going to get our values in and out and across between into our fragment pixel shader. Because otherwise you can't just send in these positions into your fragment pixel shader. It won't accept them, so you have to pass them in as texture coordinates instead, as an image, if you will. And we're passing it in as an image in memory, if you will. I know that might sound strange, but yeah, that's what we're doing basically. And then float 3 here, world normal here, and then we're going to do a colon here and text coord 1 here. So again, we're doing another setup here where we have two different sets of texture coordinates. The first one is going to be object position, second one is going to be world normals here. And we do need to do that. If you don't do this, it will not work. So very important. And of course, we're going to terminate this with a curly brace here and a semicolon. And our struct FS, or you can do PS, I don't care, out here is going to be open curly brace, and then float 4 color, colon, color, semicolon, closing curly brace, semicolon. So that's nothing new, except for the fact that we now have an FS or PS here. Okay, so our tweakable parameters. This all stays the same. This stays the same. That stays the same. Nothing new. This stays the same, and this stays the same. Nothing new. Okay, very cool. And moving on down. Okay, so now we have our VS out and our main VS, open parentheses, VS in space capital IN, close parentheses, because we're passing in our struct for our VS in. Remember, this is our VS in right here. So our normal and our position are going in to our vertex shader. Alright, so this is going to be our main VS here. Okay, so VS out and out semicolon here, and again this is our out struct, and the reason why, of course, is because we have to have our out here, which is what we're going to get passing in over here to our fragment shader, our pixel shader, whatever you want to call it. Okay, so out dot obj object here pose equals in dot position semicolon. So that passes in the position values here, and then out world normal equals multiply world itxf comma in dot normal close parentheses dot xyz semicolon. And this matters in order to get the the normal in world coordinate space and not object space. So it comes in as object space starting out for the shader here, and then we need to convert it to world space in order to get the calculation properly done with the lighting algorithm. So we do need some world coordinates, so be aware of that, and that's what we're doing here. Okay, so out dot position equals multiply world view projection comma float 4 open parentheses here in dot position dot xyz comma 1.0 close parentheses semicolon, and that gets our position here for our distortion of our view. Awesome. Okay, and then return out, which is going to return these here, and then close curly brace here, and then we're going to do our FS out main PS here, open parentheses VS out space in close parentheses, and open a curly brace here. We're going to do FS out space out. So here we're doing our pixel shader, our fragment shader out here, which has color, and that's it. That's the only thing it has in it. See, color. And again, this is what we were outputting a second ago. But remember, it's texture coordinate spaces, so we'll have to access them as such. Believe it or not. Okay. So with this in mind, we're going to create a variable P for our point, N for our normal, and L for our light position here. N dot object pose dot xyz gets passed into P. So we're just going to pass that directly in from object space here. And then we're going to normalize our N dot world normal close parentheses here semicolon. Now this is important. You cannot normalize this normal here over in the vertex shader. It will not transfer over. Believe it or not, it won't. You have to do your normalizing operation in the actual pixel shader, because you have to normalize it per pixel, and you have to have the actual vector here for the normal per face over here in the vertex shader. So you have to have your normal done in your vertex shader, and then you have to have your normalizing of your normal done in the actual pixel shader, and there's no way to do it any other way. You cannot run the normalize function inside of the vertex shader and then have it come across inside the texture coordinates. For whatever reason, it will not work. Try it in a bunch of different ways. Float 3 here, and then we have n equals normalize in dot world normal. And remember, this is our world normal coordinates where we multiplied it times our world itxf here, which is our world space inverse transforms here. Okay, and so that gives us our world normal, our normal, and basically in world space, if you will. Okay, so L is our light, and we're going to do normalize our lamp position subtracted from our point position. So this gets us essentially the distance, but we're going to normalize that distance after the fact, which just gives us nothing more than the direction to our light and none of the magnitude that we would get from a distance value formulation. Alright, so diffuse light equals max here, and then we're going to do dot n comma L, and we're going to close the parentheses here, and then comma 0, close parentheses, semicolon, and this is going to give us our diffuse light here. Calculation. Awesome. And we have this as a scalar value, if you will. Alright, and then we're going to find out our ambient color. So yeah, these have both been normalized. Your N and your L is normalized, right? Your normal and your light vector here, where it points to your light. If this is a little bit confusing because you don't remember, then I'll go ahead and launch this. Remember, N and L here. L goes to your light, N is your normal, straight up. Okay. I'm going to do the dot product of those because that falls back into this, formula here. L dot N right there, which is the same as it is here. L dot N. Okay. Cool. And then we're going to do a float 3 ambient, and this is going to be our RGB value here. So we're going to say KA RGB, which is our artistic driven control here for ambient color, which you can't hardly tell because I really don't have ambient shadow turned up much. But if I do, it will. And you can see the effect of the ambient color a lot more that way. Very cool. Turn that back down here real quick. Cool. Cool beans. Alright. And with that, let's see here. So we have our KA, we have our ambient color, and we're multiplying it times our global ambient, which is our ambient shadow over here. And that gives us our overall ambient value. And then we have our diffuse here, and it's a float 3 also. And don't forget the semicolons at the end. And it's a float 3 also for the diffuse. And it equals to KD, which is our diffuse color attribute here, which if I start moving this around, it's going to be our overall color for the object here. And I'm just going to go with red. Red is nice for now. Alright. And then times lamp color here, which is going to be our light color. So now if I change my light color, it will actually affect the color of my model. So check it out. So it's going to actually influence it. Very cool. And then times our diffused light here. So here we have the diffuse light manipulating also this by as a scalar, if you will, times this whole diffuse algorithm here. So we're determining, as it moves off the side of the model here, it becomes lighter or darker or whatever, accordingly, due to the angle of the light, if you will, from the surface. So basically, if we have the light here and we have the surface here, then we can determine how much of a light intensity it should have on that surface based on the direction of the light, and that's it. We're not doing a specular value there. That's all there is to it. So that's why you have that as a scalar, if you will. Okay. Then we go to out.color, and it equals float 4 open parentheses ambient.xyz plus diffuse.xyz close parentheses xyz.xyz again, comma 1.0 in order to create homogeneous coordinates here. And then let's just add together these two different entries together. Close parentheses semicolon. And then we're going to do a return out semicolon and then a closing curly brace here. Then we have our technique, and it's technique 0, open curly brace, pass P0, open curly brace. And of course we do our depth test enabled equals true. Now this stuff shouldn't change from the previous one. This is all exactly the same as before. But we do have something a little different here. Now, even though our vertex program is exactly the same as before, we now have a fragment program one. And so you'll need to add fragment program with a capital F and a capital P here, and a lowercase everything else, equals compile space FP40, all lowercase there, and then main PS, space main PS, here with the capital P and S. Now, I called this main PS, but if you named yours something differently, then you'll need to match that name up. Open close parentheses and then semicolon, and now it's nothing more than a closing curly brace here and then closing another curly brace here. and that covers how to do vertex lighting for a sorry, not just vertex, but vertex pixel shader lighting combination, where we have to do part of the calculations in the vertex shader, and then we can finish it up in the pixel shader, and we get a much smoother result from this. You get a much better, because remember, it's being calculated per pixel, so our light calculation on this is going to be very smooth as it goes and recesses into the shadows and such, and so it looks very nice. It's very clean. Now let's have a look at how to do this texture wise as our Lambert vertex pixel shader here. I'm going to apply that one now, and I'm going to switch over to this one. Okay, so in order to create this one, you're going to copy and paste your shader here. So select this whole shader and all the code all the way down to the bottom, and then hit Control C to copy it. Great. And then you're going to come over here to Create Effect, and you're going to create a new effect, and you're going to name it Lambert Texture _ VS _ PS or FS. Alright, so let's just know it's going to be a vertex pixel shader or a vertex fragment shader. However you want to say it, same thing. It's exactly the same thing. We don't have to do a whole lot in order to make this work, which is really nice. And I'm going to keep hitting up and going over this thing again here. As far as the pixel shader here, because this is stuff that's important to note, and it's stuff that's easily overlooked, let's put it that way. We have our world, besides our world view projection matrix, which we had from before, and of course we're still going to have all this from before too, but let's not forget, I'm going to go over it one more time here. Float 4x4 matrix is a world view, this is a world inverse transpose. We need this in order to get our world view coordinates. Not our world view coordinates, but our world coordinates. Position here. Colon world inverse transpose. Now you learned about transpose, and you learned about inverse, so you know what inverse transpose is to a matrix C calculation from before, from the matrix series. So if you don't know what I'm talking about, then you need to go back and look at the matrix math series to go over that. But basically we're just taking the world coordinate system and we're doing an inverse transpose on it. Alright, so here we have an open less than sign, and we have string here, and we have space UI widget here with a capital UI and W here, and the rest is lowercase, equals none in parentheses, not parentheses, quotes, I always say that, equals to quotes none here, and then semicolon, and then closing greater than sign, semicolon, and then we have, don't forget, we have our struct VS in. Now we're going to have something a little different here. Not only do we have something different in the fact that we have our normal and float 4 here, but we also have float to UV : text chord 0 semicolon. Now I know that this was the same from the previous shader we just did here in LamberVS PS here. But what is very different is this right here. Our float to UV : text chord 0 semicolon. And then we're close with a closing curly brace and a semicolon. Now this is very different because before we started out with text chord 0 for our object position. So now it's going to be for UV's text chord 0, because remember we're having to map a texture, so therefore we absolutely need to have UV's taking the space of the first texture coordinate system. Okay. So over here we have our struct here going for VS, going for outputting it. So VS out, open curly brace, and then we have float 4 position. Now this is a float 4 versus a float 3 for the position here for our going out, on the way out. So make sure you get that right. Float 4 position, position all caps, semicolon here. And remember, this is the position of every vertex on the model here. That's what it is. We're doing this calculation per vertex in the shader, and all these vertices are being simultaneously computated at once across the 3D card. Okay, so float to UV : text chord 0 semicolon, and that's going to be our UV texture coordinates here. Okay, and it's getting mapped to the texture coordinates, the first texture coordinates in the system here. Well, for this model, shall we say. Float 3 here, object position : text chord 1. So the second texture coordinates here system is going to be our object position here. and then float 3 world normal colon text chord 2 semicolon. So our world normals are going to get mapped to our texture coordinate 2, or to our third texture coordinate system for this model. Okay, with that we're going to end it with a closing curly brace and a semicolon. And so that's really important. And again, remember, we cannot get this stuff from here into our vertex or our pixel, into our pixel shader or our fragment shader unless we do this unless we do these texture coordinate systems here. If we don't use texture coordinates, we can't get these values in. There's no way to pass it in. So struct here, space fs out, or you can do ps out if you want. This is a fragment shader. Open curly brace, float 4 space color colon color semicolon here. And this is all caps for our color. This is standard. This hasn't changed. This still stays the same. Closing curly brace semicolon. So that's really nice. At least something's not changing, right? Okay, so we have our ambient light, and this isn't changing. This is the same from before, from all our shaders. Matter of fact, nothing's changed on that at all. And then we have our Ka value here, or our ambient artistic driven value too. And remember, this is our shadow value for our ambient global illumination. So let me just show that one more time. So you can see here, it's given our recessed darker areas of our shader, and then this is our global ambient color. And based on how high you have your ambient shadow value set depends on how much of this is affected by your ambient color. Now if I come in here to my diffuse color, I can go around and change this. Now our diffuse color is getting multiplied in to our texture also, so we actually can modify our overall shader color in addition to the actual texture color. And that's what our KD is doing. So we still have a diffuse color, and I'm combining the two. Okay, then we have our lamp position, or our light position, and our light color here. Again, this hasn't changed. It's the same thing as before. And again, the way I got to that was a Control J, in case you need to remember that. That's how you get to that hidden menu inside of FX Composer 2.5. It is difficult to find in the documentation, but that's what it is. It is Control J to get to that. Okay, so we have our all that said and done. But anyways, we have color and texture here, and we have texture space here, color texture, and this is the same as before. So exact same texture, one that we've been using over and over again, but of course we're adding this. We didn't have this in the previous one here, which is our vertex pixel shader, so we need to add this for sure. So we're going to have it type texture here. I know this might be beating a dead horse, but the more times you hear it, the more you're going to get it in your head. So hey, I don't mind going over it again. Color texture here for the name, and then open lesson sign, and then string resource name equals in quotes default underscore color dot dds in quotes semicolon. And again, resource name is capital RN here, and everything else is lowercase. I do like to have my I'm picky about this. I like to have my code blocked out like this with open curly braces on their own lines. And same thing with our greater than less than signs. It's cleaner, more professional coding method of doing this. I know some other people put this on there up here, but it's a little harder to read by doing that. So this is a cleaner, better looking setup here. So you're best off doing this because it makes it easier to visually just see something without getting confused, and make sure that you see that you're not leaving out something that's important. So if you're missing this, it will not work properly. So by having it up here, you may overlook it. So putting it here means you can visually, easily, quickly see that everything's where it should be right away. So that's important. String here space UI name here, where it's capital UI and then N and then lowercase name AME equals in quotes diffuse space texture in quotes semicolon here. And then we're going to do another one. And again, this goes into the UI name. So as it appears over here, it's going to be our diffuse texture. And of course we can select a diffuse texture if we like here. And then we're going to do a string space resource type, capital RT, and everything else lowercase equals in quotes 2D semicolon. Again, we're going to do a 2D image, so therefore we have to say 2D and let the system know that. Alright, so we're going to do a closing greater than sign and then a semicolon here. Okay. And then we're going to break out into our sampler 2D, because remember, we have to access every single pixel to be calculated simultaneously in our 3D card. So the way we're going to do that is by having this texture sampler 2D texture sampler that's going to read in our texture and then sample each particular pixel, breaking it out into the different parts of the card. So that's what this is for. So sampler 2D color sampler equals sampler state, where sampler underscore state is how you write that out. And then open curly brace, texture equals, well, it'd be less than color texture, because this is the color texture variable up here, don't forget. And then ending greater than sign, semicolon here. And then we're going to do min filter, capital M and F, lowercase everything else, equals linear mip map linear, semicolon. That is correct, that's how you write that, because we're doing linear mip mapping. Okay, and we're going to do a mag filter, and it's going to be going from this the minimum to the actual mag filter here. And it's just going to be a linear interpolation for the mag filter here. So linear. Okay, warp S here equals repeat, semicolon, because we're going to repeat along our S and T, which is the way we modify our U and V as a separate variable setup here. And so we're going to wrap S equals repeat, semicolon, that's capital W, capital S, and lowercase RAP. And then we're going to have wrap T here, capital W, capital T, lowercase RAP, equals repeat, semicolon, and close curly brace, semicolon. Awesome. Okay, and so that sets up our sampler here. Now if we're looking at our VS out here, for our VS main, our main VS here, remember VS out calls back to our out vertex construct here for our structure here, and subtype struct VS out. So this is our own custom data type that composed of position, UV, object position, and world normal as set of texture coordinate systems, and we have a position for position. Awesome. Okay, and then we have VS in here, and let's not forget what's part of that, and that's position, normal, and UVs here with the first texture coordinate system assigned for our UVs, which makes total sense, and that's why it's always been for the textures. Okay, so we're going to pass in here our VS in, and then in all caps here, in. And we're going to have closing, open and close curly, not curly, open and close parentheses around that. Okay, open curly brace here, VS out, space caps out, so that way we know the variable is out and it's just explicit, semicolon, all caps out dot object pose, and we have capital O for object here, and then capital P for pose here, equals in dot position, semicolon. So here we are assigning the position of the particular vertices of the shader of the model here, and we're applying that to our object pose out, so that we're going to be passing them through, which is important because that needs to be done in order to have them calculated in the light algorithm here for our pixel shader. Alright, so with that said, let's look at the other one. So out dot world normal. So we need to make our normal again in world space. So we're going to say equals multiply MUL. MUL is multiply open parentheses world ITX F. Remember, this is world inverse transpose matrix here. And so we're doing that, and we're going to be multiplying that times our in dot normal vector. Alright, so cool. And of course this normal here is our object space normal. So we're going to be converting basically from object space normal to a world space normal. And then we're going to have with XYZ for our return type here, which is going to be a float 3 basically into here. Okay, so with that said, we're going to do out.position equals multiply world view projection matrix here. And then comma, and this is nothing new, float 4, and then we're going to have open parentheses here, in dot position dot xyz, comma 1.0, close parentheses, semicolon. So nothing new there. We've been doing this since shader 1. You know, nothing new there at all. Out dot UV here, capital UV, equals in dot UV. So we're just passing UV straight through. Not doing anything to him, we're just passing him straight through. Technically he could manipulate UVs, but in this case we don't want to do that. Return out, semicolon, and then close curly brace. And then we're going to go to our pixel shader now. Or in this case we're saying FS out for our out structure. And what we're outputting is nothing more than the color. And that's it. And don't forget when we're going to be bringing in our VS out, which is going to be our position with the position value here for basically position of all the vertices in the side of the model. And then we have our UV here for our map to the texture coordinate 0, object's position map to texture coordinate 1, and world normal here map to texture coordinate 2 space. So don't forget about that texture coordinate spaces here. Okay. So with that, we have our FS out, and we have our main PS, which is our pixel shader here. Open parentheses, VS out, and then space IN, close parentheses. Alright, so that's going to be passing in the values that we exported from our vertex shader, and it's going to be passing them into our pixel shader. Okay, and then we're going to do open curly brace here, and we're going to do FS out, out, so that way we can output what? The color. That's right, semicolon. So float 3 here, P, remember this is going to be a point on the surface, equals in.objectPose.xyz. So as a real quick refresher of what I just said, wrong thing. Okay, alright, so yes, the point position would be this point right here that our normal vector is coming off of, and our light vector here pointing to the light is where it's coming from. Okay, good. And that brings up the point of N, which is our normal. It's been normalized, awesome, so that means we end up with just the direction because it's been normalized. Open parentheses here, in.world normal, close parentheses, semicolon. Remember, it's world normal because we multiplied it times the world inverse transpose matrix here. Alright, so now we're going to come over here to our float 3, L, which is our light direction vector. Now it is a direction vector with magnitude here when we do our lamp post position, or basically our light position, minus our P, which is our point position on the surface, right? An object space. Don't forget this is an object space and not in world space here. Okay, and when we subtracted those, then we end up with it normalized, and we just get the direction here for it. And then that ends up being L. So float here, diffuse light equals max dot product here of N dotted with L. So but these are been normalized, so we end up with what? Just the direction. That's right. So N dot L gives us the direction vector value here. Well, that'd be they're both directional vectors getting dotted with each other. So let's put it that way. And that ends up being a resultant value from there. And then that's going to be your maximum, and it's going to go down to a minimum of a 0 here. And then it's going to be closing parentheses, semicolon. You cannot have a negative value here, so that's why we're doing a max with whatever this value comes out to being as our maximum, and down to a 0 for interpolation purposes. Okay, so float 3 here, ambient equals ka.rgba, .rgb times global ambient.rgb semicolon. Now if you remember right, this is going to be our RGB global ambient here. RGB is going to be our IA, if you will, or I ambient, and this is our shadow value here, if you will, or our fall off shading, if you will. That's another way to put it. Alright, and then the other part here is our ambient color, which is RKA, and that's what that is right there. I just manipulated it. Okay, and to do together, make it do that. Alright, so that gives us our ambient value by multiplying these together, these two vectors together, or color values, let's put it that way. Alright, so float 3 here, diffuse equals kd.rgb times the lamp color, or our color of our light, times the diffuse light here. Now if you remember, diffuse light here is a magnitude of our, well, shall we say a scalar, if you will, right? So if it's within the angle of the light, and the light is facing towards the surface here, then as the light hits the surface, it's like in direct alignment with the light, then you're going to get the brightest value. Then as it falls off here to the edges here, you can get a darker and darker value, and that's exactly what this light diffuse scalar is basically doing. Just doing a light to dark value here. Okay. And then again, KD is our diffuse color. So if I go in here, I can change this around. What gets a little more interesting here is after I do this, we're going to do out.color equals text 2D, and in parentheses here, color sampler, comma, in.uv, close parentheses, times float 4, and I'm just multiplying this times our ambient.xyz plus our diffuse.xyz, and then doing a .xyz after it, and so I come back with a float 3 when it's all said and done. far as this comes right here, and then we're doing comma 1.0 and to get non-homogeneous coordinates. That all is getting multiplied times our texture color here, and so when we change the color here, it will actually be applied across our ambient and diffuse color and our overall color contribution here. So that's very cool and important aspect of this. Okay, now we drop down to our return out semicolon in order to return out the color. Remember, that's what's coming out of this thing here, is the actual color. Yep, right here from the struct, the only thing in that struct is color. Okay, return out semicolon, close curly brace. Technique space technique 0 here, open curly brace, pass P0 here, open curly brace, because we only have one technique here and we only have one pass that we're doing. You know, so that's all there is to it. We're going to do our same old depth test enabled equals true semicolon. It should be the same as from before. Same thing for depth mask, cold face enabled, blend enabled, and depth func with a L equal or less than or equal to. Don't forget, L equal means less than or equal to, semicolon. Here, so vertex program equals compile VP40 main VS open close parentheses semicolon here, and that lets us compile our vertex shader. So if I come over here to my vertex shader, here it lets us compile this shader, right? And don't forget, we're not passing anything in. Alright, and then we have our fragment program equals compile FP40 main PS open close parentheses semicolon. Yes, we were at the final end of this here, and that lets us compile our pixel shader, or if you want to say fragment shader, if you did FS here instead of a PS, or maybe you have some other name for it, but main is a good name to have in this, so we know that this is the main pixel shader, and not it helps if we have multiple functions above and beyond just our main vertex and our main pixel shader, and as we move into the future we'll run into that more and more. Okay, so semicolon to end that off after the open close parentheses here, and then a closing curly brace and another closing curly brace after that. With that said, that covers both sets of shaders, both our texture based vertex and pixel shader, and our for Lambert, and then our regular Lambert vertex and pixel shader with no texture capability in it. That covers it. And with this, you now have enough knowledge that you know how to do a Lambert shader, and then if you want to, you could apply the other techniques you learned from the previous videos for how to do crazier things with shading and textures, for mixing things up and multicoloring things with mathematics, swizzling, etc. And you can mix all that together with the light model to create even crazier and cooler, better looking scenarios and shaders to give you the most amazing looking thing as much as possible, shall we say. As we dive into the series more and more, we'll go into more and more light models. We'll be covering other things like reflection models and all this wonderful stuff to make it look even better, environment reflections, etc. And we'll just keep moving forward and making things look more and more realistic and look better and better as we get into more and more complex methods of doing things here. But this gives us a nice basis. As the very first light model you want to cover is Lambert, and this is the simplest one of them all. Next, we're going to go to Phong, which is the other like cream of the crop core, shading light model here that you'll always use over and over again, for that so many other light models are based on. And so once we cover these core ones here, you're going to see there's very little difference between this and the other light models. You get the certain look you need, and it's just little variations of these different light models. So very cool, very powerful, and awesome nonetheless. Okay, so with this covers Lambert texture, VS and PS for vertex pixel shader, and our Lambert vertex and pixel shader. My name is Nate Nessler, and this is for Hyperactive Studios. Thank you very much.